So now we're moving on to the sun. Life would not be possible without the sun. We get all of our energy and heat from the sun. Now, people call the sun the average star. If you watch the video, you know it's pretty much not the average star, but it falls in the average position of all the charts, and that's kind of our fault. We compare everything to what we know, and so we know the sun, so every other star we compare it to what we know, so kind of like, well, you're an average star because you fall in the middle of all the charts. Well, we kind of put it there, setting the sun as one unit or one solar mass or one whatever. The sun is held together by a combination of gravity and nuclear fusion. So gravity wants to pull everything into the sun, but the nuclear fusion at the core is trying to push everything out of the sun, and so they're in a balance. This is the chart from your textbook about the sun. Gives you the radius, the mass, density, blah, 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 surface temperature, luminosity, all that fun stuff. Alright, so in order to figure out the luminosity of the sun, you actually have to assume that the sun's giving off light equally in all directions. So it doesn't matter where you are around the sun, you're getting the same amount of light because it's giving off the same amount of light. So in order to do that, you do a bunch of calculations, blah, blah, blah. Your luminosity is 4 times 10 to the 26 watts. That's a lot, right? And if you want to write that all out. Or it's basically 100 billion 1 megaton nuclear bombs a second. Either way, my brain can't wrap around either one of those. Just a lot of energy. Alright, so the sun doesn't change much. Its temperature pretty much stays the same, its mass pretty much stays the same, the radius stays the same, the luminosity stays the same. Now, that being said, it does change. However, this change takes billions of years. So for us, the sun was the same yesterday as it is going to be tomorrow. Like I said before, there is a fight between gravity and fusion, right? One's pushing outward, one's pushing inward. And this balance is called hydrostatic equilibrium. All right, so the sun, if you look at the picture there, you'll see it's blue and red. Like, what? Our sun's not blue and red? Different wavelength, right? So this is actually a Doppler shift. So blue and red shifted moving away, blue shifted moving towards. That means there's areas in the sun moving towards us and moving away from us. So the surface of the sun actually vibrates. Kind of strange. And we can get something like seismic waves to study the inside of the sun. There's a whole science on this called helioseismology. So the study of the surface waves on the sun. So there's different groups that study the sun and its waves, and they've come up with a model of the sun. They learn about its temperature, its density, the rotation, the convection cells within the sun, and they came up with this model. And once we were able to actually study the sun, this is pretty incredible. Their model, with what we now know for sure, are within 0.1% of an error. 0.1% of an error. That's incredible. So the sun has this global circulation pattern. Basically, gases move from the equator to the poles and back to the equator. Takes about 40 years to go around this loop, equator, pole, equator. Now, if it wasn't for our land surface on Earth, we would have the same circulation pattern. So, kind of interesting point there.